The de Broglie wavelength, though, again, to be clear, it's not physically saying the particle is moving up and down. It is saying that just like the phase of the electric and the magnetic fields for a photon, there is the possibility of there being an equivalent phase in whatever medium we don't know. And we'll come back to that question later because that is a super strange trip of your mind. But there is some phase associated with a moving particle that the importance of that, as we know, when you have a phase associated with that, you have the possibility of interference. And that's exactly why we're going to apply this now to the Bohr atom. If you start viewing particles that have a changing phase as they move forward, and by the way, I have a prop. Here's how I think of this. This is a oven thermometer, and as you spin that, if the background was white, it just kind of looks like there's a dial going up and down. And this is the best way to visualize what I mean when something moves with a phase. As it moves forward, it's kind of like the dial is rotating, and if it moves back, the dial is rotating the other way. So the phase you can think of as just simply a number. That number goes up and down as the particle moves forward in a line. I think it's kind of a cool analysis there, or a cool interpretation. So instead of thinking like that, think of it as just a dial that changes in a linear fashion like that. And wherever that dial is, if there's another particle there with the dial exactly opposite, they will cancel. So that's what's going to happen here when we talk about electron cancellations and whatnot. We think of it specifically as there is the possibility of cancellation if the phase of something interferes with an opposite phase. Now let's go back and apply this to the Bohr model. So what I mean by this, and actually let me be a little more clear. So if we imagine an electron traveling around in a circle, with the radius of that circle somewhere on the order of the de Broglie wavelength. I don't mean it's precisely the same. I just mean that they're the same scales. So there's a couple options. There is one possibility. So we have that electron here, and now when I draw the de Broglie wavelength, I am gonna kind of pretend like it goes up and down. So let me make the best circle I can here. And then, actually, that's pretty good. Fair enough. And I'm just going to kind of play a bit of a guessing game here. So imagine that de Broglie wavelength, is something like this. So it's going around in a circle. Wow, that couldn't have gone any better. But so basically, if you take this whole thing, and if it was previously a line like this, and this is what I've just done in my head, I've imagined an electron traveling a straight line with that de Broglie wavelength, and I've just connected those two ends of the line together. So that's what I was going at with this. And the exact way that I just drew this shows that there's a possibility of if the phase, now remember the red line is indicating the phase. If the electron starts with a phase as maximum and then dips to a minimum, maximum, minimum. Now in this case, it has gone up and down once, twice, 3 times, 4 times, 5 times. In this case here, if you take this circle and you stretch it out, that would correspond to precisely 5 de Broglie wavelengths of that electron. What happens when this occurs? Remember, this electron is traveling at a mildly relativistic velocity. And so it does this literally millions, if not trillions of times a second. Now, if that maximum that it started from does not perfectly line up with the maximum when it comes around again, what do you think is going to happen? The way to kind of draw that out is to actually view it as being in a straight line here. So, again, my question that I just posed is, if you view it as if you stretch it out as a straight line, but then just in your head connect those lines, it would look like this. So there's 1, 2, 3, and I'll just do 4 here. Yeah, so there's just 4 there, but whatever. So in this case here, it gets to the end, and then we have to kind of loop back around here. It goes there, 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 back again, starts again. Now, in this case there, the way I've drawn it, and in this case there, the way I've drawn it, when it finishes one complete length and it starts the next, it's at precisely the same phase. Let's compare that to a different situation, and this is where my artistic abilities will ruin everything, but it will look something, I guarantee I'm going to screw this up. Actually, no. There, okay. I'm going to do it like this. Yep. All right. There we go. That's what I want to do. So in this case here, the green line indicates that in one circumference, which again, wrap those around in a circle. In one circumference here, this electron, if it had a slightly longer de Broglie wavelength, it would make 1 wave, 2 waves, and then a half. So after one circle around, it's at the opposite phase. Now it starts right there. And then at this point, the second time I'll draw it in a dotted line here, it'll go like this. And then it loops back around, now it starts this again. Can you see exactly what's going to happen? If you do, you have just fully understood the Bohr atom. Because in this specific case here, the fact that the de Broglie wavelength was a half integer multiple means that it goes around once and has a maximum there. The second time when it goes around, it's going to have a minimum there. And we know full well when objects travel like waves, if one maximum intersects with the second minimum, they cancel. And that's exactly what would happen. Every point along this, that second lap through will have exactly the opposite phase of that first lap through. And at every point along there, if you let it do this over and over and over per second, it's almost like it's canceling itself out every other trip around. And the effect of this, if you view it on longer timescales than just 10 to the minus 10 seconds, the effect is that the electron perfectly cancels itself out everywhere. That's why electrons cannot orbit at just arbitrary distances from the nucleus. And this is the heart of the Bohr atom. Once we take de Broglie's idea and we accept that electrons or massive particles can have a wave, we necessarily have to accept that electrons can interfere with themselves. If they come back to the same point at a different phase, we're naturally going to get a destructive interference. So if I had drawn this circle slightly bigger, and if I had done that exact pattern here, and I'll actually do that. I'll do that in a second. But if I draw this with a circumference that's like a half integer of that wavelength, every other time the electron comes around, it'll cancel. And so it's as if, basically it means that the electron is simply not able to orbit there for a long period of time. It might go around once, but things don't do that just once. On times, if you look for a whole second, it's done that 10 to the 20 times, 10 to 18 times or whatever. So the point is that if that first peak doesn't match up with that second peak, if you let this go numerous times, you're guaranteed that the macroscopic result over measurable time periods is going to be perfect destructive interference. Even if that second peak is slightly offset, what you're going to have is that peak slowly migrates every time around, and you're guaranteed that if you wait long enough, every 3 laps it will cancel, or every 8 laps it will cancel or something. unless that phase perfectly lines up with the peak phase at the beginning, you're guaranteed that you're going to have cancellation over numerous laps.